Hi, everyone. So I suppose we should be alive. Please let me know if you can hear me and see me all right. And let's give a minute for everyone to join. Meanwhile, I'll prepare the slides and we will start right on time. Awesome. See if people can hear me and see me. That's great. I'll just share my screen. And yeah, as I mentioned in the introduction video, I will answer all the questions after the lecture. So, but feel free to write them in the middle. If you see something, I will go through the chat afterwards and see if there is anything. So let's start and welcome everyone to the first lecture of my Haskell course for beginners. I'm really happy that you all are here, and I'm really excited that you are eager to learn functional programming in Haskell. So let's start. So functional programming, or FP for short, what is this? What is this beast? So, I mean, the name suggests that it's somehow related to functions. So let's first understand what is a function. And in math, a function is a straightforward object. So it has like a name, and it has some arguments, some input, and it says what it returns on this input. And for example, in this case, we say that f of x equals to x squared. So this is a function that takes one argument and returns some value. However, functions in programming are not like in math, and unlike math, they can do other things that functions in math can do. For example, functions in programming can loop indefinitely. They can work forever or just take a very unreasonable time to compute, so very long time. Math doesn't care about how long it takes to compute its function. It doesn't have the notion of computation, but in programming we care about this. Moreover, functions might hang or loop not only like by accident, just because of some bug or error, but intentionally. For example, if you have a web server for an application, it's actually not supposed to stop. It's supposed to work indefinitely. And if it stopped, probably something bad is happening. So yeah, some functions are supposed to work all the time. Also, functions in programming can have side effects. So they can read from files or maybe send requests to some servers over the internet. Functions in math can do this. So we need to care about this stuff. And because of this, functions in programming can throw exceptions. For example, if you have a if you try to read a file and you don't have such a file, so you throw exception. It's some situation that you haven't handled. And also functions can terminate early. In programming, we have resources like memory, and if functions take just lots of memory, so they will terminate early because there is not enough memory to compute them. But math doesn't care. So, but still, functions in functional programming are trying to be like very close to the definition of function in math. So not exactly the same, so just keep it in mind, but still very close. So what is functional programming? So there is no standard definition like accepted by everyone. What is functional programming? There are very vague different definitions, but the main point of functional programming is the focus on functions. So function is the main building block of functional programming. And what it means is that in functional programming languages, it should be as easy as possible to create new functions, to call functions, to combine them, to compose, to define new functions using existing functions. You can use functions as arguments to other functions. You can inspect functions, basically do everything with that. So unlike object-oriented programming languages, where it's easier to work with objects. So it should be easy to create with objects, but in FP, it should be easier to work with functions. And there are different functional programming languages, but there are some FP concepts that are kind of similar, maybe shared by different languages. And these are the main of them. The first one is the most important, is the higher order functions. This means that functions can take other functions as arguments, as their input. This is a very important concept. And we are going to talk about this today. Also, functional languages have algebraic data types, is a way to create very flexible data types. And it's very helpful. And we're going to talk about this on the second lecture. So once you have algebraic data types, you might want to have pattern matching. This is the ability to describe patterns for your inputs and how your functions behave on these patterns. This is also a really important concept. Additionally, functions in functional languages are pure usually, and it's encouraged to have them pure, which means that pure means they don't have side effects like reading from files or sending requests. So this makes functions closer to the mathematical notion of functions. Also, all values in functional languages are usually immutable, and immutability is encouraged. Immutability is when you can't mutate variables, you can't change values. And it might be difficult to understand this at first, but it actually makes some things more robust and more reliable. And we're going to talk about immutability today as well. Another concept is totality. Totality means that functions work on all inputs. So they don't hand, they don't throw exceptions, they don't have some cases that are not covered. And that's also an important concept. And finally, laziness. So it's not usually like a concept of all functional programming languages. So Haskell is, I guess, the only kind of popular language which is lazy by default. And again, we're going to speak about this today. But usually in functional programming languages, laziness means that you work with some infinite streams of data, and the streams have some events, and you want to process them, and you want to process them like lazily, like when the events come, you want to process them. So this is usually what it's mean by laziness in functional programming languages, and you actually, they're pretty good at this. So these are the general functional programming concepts, but besides that, Haskell has its own features. So it's a statically typed language. Not all functional programming languages are statically typed, but it has statically types. So you need to write types of functions and expressions in the code explicitly. And Haskell has polymorphism. So you can actually write types of functions that work not only just for single type, but for different types. And this is very handy. So you don't need to write boilerplate code. You can just write polymorphic functions. Also, on top of that, Haskell has type inference. So you need to write types, but you actually don't need to write it all the time. So Haskell has type inference, and which means that it infers types of expressions for you. You don't need to specify types everywhere, just only like in important places and relevant. There are some syntactic features of Haskell, so it's layout sensitive, which means that you don't specify blocks of code with curly braces. You specify them with same indentation, like in Python. Also, Haskell is coming from the so-called ML family of languages. So ML is short for meta language. And most of the mainstream programming languages, they have C-like syntax. So Java, C#, Python, Ruby, JavaScript, they're like in the same family. But there are other family of functions, NML like Haskell, OCaml, F#. They have different family. And this is the thing that makes also Haskell kind of maybe difficult to learn because it has different style of syntax. Haskell also have automatic array, and we're going to talk about this today, which means that you can apply functions partially and get also other functions. And you don't need to have extra syntax for this. It's not true for other languages. But these are the programming like type level or maybe some program level features. But Haskell also has its own runtime system. And its runtime system has a garbage collector. So when you allocate new values, you don't need to worry about memory management. Haskell does this for you. You can create threads, and Haskell has green threads or so-called lightweight threads. which are like don't occupy lots of memory, and you can have thousands of those threads without worrying about memory consumption. And also Haskell has software transactional memory, which is kind of neat concept when you want to have atomic operations. So Haskell kind of pushes this functional programming on the concurrency, and all the functional programming concepts are really important in concurrent programming. So before we talk about Haskell itself, let's talk about Haskell Toolchain. These are the main tools in the Haskell ecosystem. So the main one is a GHCi, which is a Glasgow Haskell compiler. And this is a compiler for the language. It takes your code and it produces the program that works with it, and also does some of that. This is the main compiler. There is GHCi, which is interactive interpreter, and we are going to work with this a lot. There are two build tools in Haskell called Cabal and Stack. So you can have one file, but then you have multiple files. You may want to organize those multiple files in the projects, and you may want to use projects by other people. So this is where you want to build tools. So Cabal is the first one, and Stack appeared later. This is what you need to use. HLS is a Haskell language server, is an implementation of a language server protocol for Haskell. So basically, if your IDE has language server support, you can have Haskell support out of the box. This is kind of mostly the main supported IDE in Haskell at the moment. And finally, there is GHCi, which is a tool for managing all of the above tools. So you just usually install GHCi and you can install everything else with it. And you can set versions, you can set default versions, kind of managing all the stuff. So once we have familiarized ourselves with the toolchain, let's start with the Haskell. So the first one is GHCi. GHCi is a REPL, and REPL is short for read eval print loop. What it means that it's an interactive interpreter. You write something inside it, and you immediately get the feedback of evaluation of what you write. So you may call some functions and do some computations, and you will get the result immediately. So it's like reading your input, evaluating your input, and printing the output. And doing this like step on the step. This is what does it mean. And you don't need to install GHCi separately. If you install GHC with GHCi, you get GHCi out of the box. So you run it into your terminal and you can type it immediately in the terminal. And we are going to use GHCi a lot in this lecture and presentation to see how Haskell works. And the convention of the slides is that if there is some command in terminal, it will start with $, which means that I'm calling outside of in the shell. But if it's GHCi command, if it's like Haskell expression or something like that, it will start with a prompt like prelude arrow or GHCi arrow. So this is a prompt where you can start. And let's start with fundamentals, with the basics. So in GHCi, you just type you can type arithmetic expressions, for example, 3 + 4, and the GHCi will immediately type you an answer, which is 7. So you can do all the basic arithmetic operations like addition, negation, multiplication, division. And if you want to use negative numbers, you put them in round brackets. So Haskell don't mix it with the subtraction operator. You can use multiple operators, and Haskell will put implicit round brackets for you. We all know from school that multiplication has like higher priority than addition. But if you want to have your custom ordering of operations, or if you want to be more explicit, you can put your round brackets manually. This is just basic arithmetics. Like you can use power operator, and if a result of your application is like it's floating point number, Haskell will deduce this automatically for you, and you will get like a floating point result. This is basically arithmetic. I actually often use GHCi just as a quick calculator, and still I just type some numbers if I want. Okay, Haskell also have comparison operators, like all the basic stuff there. If you want to check two values for equality, you use the equal operator, and GHCi will print you false if it's not the result is false, if it's not true, or true if it's again true. And not equals operator is slash equals. So it's kind of like mathematical when you put slash on top of the equals, but you in programming you put it before. This is just checking operators, and there are comparison operators like less, greater, less or equal, and greater or equal. This is just some basic operators and standard common functions that you use with Haskell to compare values. Also, you can like combine different values if you want to check if both your conditions are true, so if you have two expressions that returns true or false, you can use like double ampersand operator, which says that they both should be true, or you can use this operator, which is like AND operator, or you can use the OR operator, which is a double vertical lines. It says that at least one of the expressions should be true, and it will return true. You can chain these operators if you want to have multiple expressions. You can use values true and false directly. So we don't necessarily need to produce them from other expressions. You can use them directly. These are just plain Haskell values. So these are just some basic operators, but Haskell has functions. And by default, you have access to some functions. And there's the syntax of calling functions in Haskell is the next. You put the name of the function in the beginning, and then you put all arguments to this function separated by space. So no commas, no round brackets. For example, if there is a function not that takes a boolean and returns the other boolean. So if not from true, it equals false. So we just pass it another argument in a separated. There's function division, integral division. And if we divide integral 7 by 3, we get 2. Again, we have two arguments and we just separate them by space. But sometimes we may want to group arguments. For example, this 2 multiplied by 3, it's a single argument. So just to help Haskell to understand this is the one argument, we put it in round bracket. This is how we group arguments. So the function max, it takes maximal of 2 values. The function min takes minimum of 2 values, and we can use nested functions inside. But we don't want to skip this round brackets. Like, it's really important to remember. And again, I want to emphasize this. So depending on how you put parentheses, the values can change. So if we just, in the first example, we divide 7 by 3 and we get 2. And then we add 2 and we get final 4. This is how the result is composed. But in the second example, we first add 2 and 3 and we get 5. Then we divide 7 by 5 and we get 1. So round bracket is important. If you skip the brackets and if you put them in the wrong way, you will get an error message, and it will look very scary. So, but what it means is that you haven't passed enough arguments to div, but because of how Haskell works, how types works, the error message doesn't say exactly that, and it may look scary. And if you don't understand it, it's totally fine. I mean, it's some gibberish. It doesn't make sense for now, but sometimes if you see some errors, just check if you pass enough arguments to your functions. So just some practice basic syntax, and let's go to types. So as I mentioned, Haskell is a statically typed language and strongly typed, so which means all expressions, all values, they have types. And usually when you want to specify a type of expression, you put expression on the left, you put double colons, and you write the type. And in GHCi, there is a special command :C, which is a short for colon type. You can use both, either of them, which tells you the type of an expression. For example, if we check what is the type of true, GHCi says it's true has type boolean. Okay, what is the type of false? The type of false is also boolean. And what is the type of a character F put in a single quotes? It says, okay, its type is char. So char is a type for characters. So you can think of a type as a like set of possible values. So all values have types, and types just tells what values it belongs. So different types might have different values. And if we want to check the type of a bool, we see an error message. So it means because we cannot check the type of a type because types don't have types, only values have types. The error message says something, maybe not something different, but what it means is that there is no such variable, and we cannot have when we cannot expect this type. Hope that makes sense. So, but there is one catch. If we check the types of numbers, we will see something unexpected. So let's say we want to check the type of number 21, and we won't see like some type. We will see this like double arrow. We will see a variable p on the right side, and on the left side, we will see something like num from p. So, and you might wonder what is happening here. So what does it mean? Well, in Haskell, numeric literals, like these numbers, they're polymorphic by default. So this is made to, so these numbers can mean different things. So things are by default very polymorphic. So and you may get hard times, but what you can actually do when you inspect types of numbers, you can add this plus D option and you will get some type. So plus D is a short for default. And well, when GHCi calculates types and computes expressions, it eventually needs to use some specific type, some operations. And the plus D option just tells you which one GHCi will be used. So if we are having like an integral number, GHCi will tell us it has integer type. If it's a floating point number, it's by default double. These are the types of the numbers. So just keep in mind, and let's assume for now that these are the types of numbers, even though they're polymorphic, but we will get into that in the next lectures. Okay, we check the types of simple expressions. Let's now check the types of functions. So if you check the type of function not, you will see that, okay, not, there is an arrow and there is bool on the left side of the server and the bool on the right. So what it means is that there's a function that takes a Boolean value and it returns a Boolean value, just takes a single argument and returns a single result. Well, it makes sense, not of a single Boolean value. And if we inspect the type of div, again, it will have some these variables, lowercase letters. And you can, if you see this, you can try to add plus D option and check if the new type will make sense. And we see the diff is a function that takes two arguments. So it takes integer and another integer, and it returns integer. Okay, it makes sense. We just divide two integers and we get another integer. These are the types of functions. And in Haskell, operators are also just functions. So they're not special constructs of the language. They're just plain functions, just written using operator symbols. So what are exactly operator symbols? It's written in the Haskell standard. So it just specifies all the possible symbols. But double ampersand is a Boolean operator, which is just function. It takes two Booleans and returns another Boolean. The subtraction operator is also just a function. It takes two integers and returns another integer. So it's quite simple. If you know how functions work, you also know how operators work. So the only difference is that you can put operators between your arguments, while in case of the function, you put function at the beginning and then all the arguments after its name. That's basically the only difference between operators and functions in Haskell. So we talk about some primitive, simple values, but there is another very important data structure in Haskell, which is list. So list is a sequence of elements, and it's used a lot, and we're going to use this a lot. So let's get more familiar with this data structure. So list literals is just sequence of elements, just list of elements, and the empty list, you just square brackets without anything in it. So, but if you want to put some elements in the list, you specify them between square brackets, but you separate them by comma. So on the second example, we have a list containing 3 elements, like 3, 1, and 2, and you just separate them by comma. And the next, you can put expressions. I mean, in GHCi, you can have some expressions as elements of the list, and GHCi will kindly evaluate those expressions for you when it will print the final result, final list. And there are also special operators to work with lists. So if you want to append to list, if you want to concatenate them to add the second list after the first one, you use a plus operator. So not plus, but plus, double plus. Plus is only for appending numbers, but double plus is for appending lists. There are 2 different operators you need to remember. And there is another special operator called colon, which takes an element on the left side and a list on the right side, and it prepends this element. So basically inserts it into the beginning. It's also a very useful operator, and we're going to use this a lot. And again, types are our friends. So I just inspect what is the type of list, how it looks like. So if we create just list of booleans like true, false, true, and we inspect its type, GHCi tells us that it's a bool put in square brackets. So what it means when you see that something is put in square brackets, it means in Haskell that it's a list of values. So it's a list of Boolean values. Okay. If we inspect the values, if we inspect the type of list of characters, again, we see this type, it's a char put in square brackets. So it's a list of characters. Yes, makes sense. Just list is the type of element put in the square brackets. This is what it means. So let's familiarize ourselves with basic and fundamental Haskell functions to work with lists. So first of them is this four functions. Head, it takes the first element of the list. Tail, it returns the list without the first element. Last, as the name suggests, takes the last element of the list. And init, it takes all the elements without the last. So there is a picture for better understand it. These are very important functions. The beginnings are very helpful. And it's really nice that they all have like 4 letters long. All good functions are 4 letters long. But actually, those functions are not encouraged to use because they throw exceptions on empty lists. For example, head takes a list and returns its first element. So what happens when we give it an empty list to head? Well, we see an exception. There is no first element in an empty list, so we get an exception. This is actually problematic. Lots of people have this exception and they don't know where it's happening in their code. And that's why it's suggested not to use such functions. In Haskell, it's always possible, according to my experience, to write code in such way that you never need to use these functions. Well, we might use them in the beginning for now, as we haven't learned all the Haskell features and all the syntax. But in general, just no discussion, you should be careful when you're using these functions. Just a heads up. Okay, so there are more functions to work with lists. For example, the function reverse that takes a list and returns a new list with reversed elements. Very helpful. There is function take. It takes a number and a list and returns the first elements of the list with the size of the number. So take 2 returns the list with 2 elements. A drop function returns list without the first 2 elements. So drop 2 returns. Null is a function that returns Boolean value whether the list is empty. So if list is empty, it returns true. If list is empty, it returns false. So it's not related to nulls in other programming languages. It's just to check whether the list is empty. Another helpful function is lm. Again, as I said, all good functions have 4 letters, which is great. So it takes an element and it takes a list and it checks whether this element belongs to the list. So lms, in this case, the character X is not in the list of characters A, B, and C. But lists can also contain other lists. So there is nothing wrong with having a list of lists. And there is a function concat that takes a list of lists and it just flattens this list, just concatenating all lists in all this list, and we give not a list of lists, but just a list of elements inside. This is how concat works. Other functions are usual stuff like length. Length returns the number of elements in the list, as the name suggests. And there is this double exclamation operator, which is like index operator. It returns the element of the list by the index. So element indexes of list in Haskell start with 0. So the element by the index 0 is just 5, so first element of the list. So same these 2 functions, again, they are not recommended to use because they're very slow. So length doesn't return your length immediately. It needs actually to walk through the list to calculate length every time. So that's why length is slow. And the same is true for the double exclamation operator. So lists in Haskell, they're not more efficient kind of like stream insets when you consume elements one by one, but they're not great for such kind of operations. And again, we will understand better why this is happening, but just for now, you might want to use this function. So it's like you don't need to be paranoid and avoid it at all costs. But generally, if it's possible to write code without using these functions, it's usually a good thing to do. Okay, there is a nice syntactic feature called list ranges. So it allows you to create elements from one element to the beginning. So you just put double dots between 2 elements, for example, 1 dot dot 10, and we have a list of all elements from 1 to 10. We can specify a custom step, and how we do this, we specify the first element and the second element of the sequence, and Haskell calculates the difference between the first and the second element, and it will increase the second element by this difference until we reach the final element. So if you want to have the list of all odd numbers from 1 to 20, we just write 1, 3 dot dot 20. Just nice syntax construction. It doesn't work in the opposite way. So if you want to have a list of ranges of elements from the 10 back to 1, like 10, 9, 8, even if you just write like this, we get an empty list. And this is happening because the step by default is +1. So we get 10, Haskell tries to check 11, and it says, okay, both 10 and 11 are like greater than 1, so we just return an empty list. So if you want to have a range in like opposite and reverse order, you need to specify the previous time like 10, 9, and only then 10. And then the step will be -1, and you will be good to go. So this is just a nice way to create some sequences of elements going one after another, and we are going to use this syntax a lot. And what is cool, that in Haskell you can actually have infinite lists. So if you just write 0 ... nothing, just square brackets and close, you will get an infinite list of all numbers from 0 to, well, to the last number. I mean, there are infinite number of numbers, so you don't get this list. And if you try to print this in GHCi, you will see that GHCi will just print all numbers one after another without stopping. So how does this work? This is actually works because Haskell is lazy. And let's look more into lazy. So a lazy evaluation means that values are evaluated only when they're needed. So what does it mean I need it? Well, I'm kind of using this vague term needed. I mean, in Haskell, people like formal definitions, and there is a formal definition what does needed means. But for now, let's kind of be more intuitive. So in our case, needed means, I mean, we want to evaluate in GHCi, we want to print the result. So if we print the result, it means the value is needed. So if the value is needed and everything itself needs to calculate it, it also will be evaluated, but nothing else, so not more. And which is great because it will save our computation times, and it will also allow us to have such cool things as infinite data structures. So for example, if I apply function take 3 to infinite list from 0, I will get just the first 3 elements of an infinite list. And I don't need to store this infinite list of numbers in memory, which is great because I don't have infinite memory to store infinite lists in my laptop, but I will get the result immediately. And I can apply functions in sequence, and they compose nicely. And I will also get the rest. So for example, if I drop 5 elements from the infinite list, then I take 3, I will get all the elements from 5, 6, 7, all the 3 elements. So this works nice. Another consequence of laziness, not consequence, but another feature. For example, we have a list of some elements. So this is a list of 3 elements, 5, then head of an empty list, and then 7. So if we try to print this list in GHCi, we'll just evaluate as it is. We will see that open square brackets, 5, comma, and exception. So Haskell tries to print the list from the left, and it sees that head of an empty list is an exception. So it just stops this exception. But if I just take the second element of the list, I mean, starting from the index 0, 0, 1, and second, so the third element, I will, oh, there is a typo, sorry. It should be 7, not 5, it should be 7. Second element of the list is 7. So actually, there is no exception because I don't need the value head. I just need the other element, like 7. And this is great because I mean it's not evaluated, so I can deal with this later. I can deal with this value, and this is what means by lazy evaluation. So we only evaluate values that we need, even because 7 is after of the head. Haskell just walks past this head evaluation. It doesn't try to evaluate, so it doesn't care. I mean, I don't need it, so I don't care. Just leave it as it is. There are some consequences. So because like lists can be infinite, so if your functions work lists, you now need to think that does it really work with infinite? So not all functions work with infinite lists. If you try to calculate the length of infinite list, your computer will hang because I mean it's not possible to calculate the list of the length of an infinite list. It will hang. So that's why also length is not encouraged in functions, because your functions can take infinite list and length will just hang. So just try to avoid. But if you know that list won't be infinite, so there is no harm. So another important data structure in Haskell is string, and in string in Haskell is actually just a list of characters. So if I inspect the list of like characters put in single quotes, comma separated between square brackets, the type will be list of char, the characters. But if I just put the string between the double quotes, hello, its type also will be just char. And this is, on one hand, Haskellers don't like this because list of characters is not really an efficient representation of strings. So if you want to have, like, if you want to do something in production, if you want to worry about memory and performance, there are better ways to represent strings, and this is not far the best way, but it's great for education because, well, string is just a list, and you already know lists, so you can just use all the functions that work with lists on strings. So take, it works with lists, so you can just use it with strings as well. Just take 5 hello takes, returns you the string containing the first 5 characters. You can use the same plus operator to append to strings, because strings are list, and you use plus to append the string to list. There are also specific functions to work with strings. So there's a special function show that takes a value and converts it to a string. So it's a polymorphic function. Again, we'll talk about it later. But there are also functions that, like words, that take a string of words separated by space, and it removes all spaces, or like line breaks, and it returns a list of strings without those spaces. Or the opposite of this function on words, it takes a list of strings and it puts a single space between those words. This is the kind of neat functions to work with string. So we familiarized ourselves with basic values, types, and we're now ready to write some real Haskell code. So let's create our own functions. Let's start writing our own functions and writing more Haskell. So the syntax of defining a function is the following. You write the function name, you write double colon, and then you write type of the function. Then on the next line, you write the function name again, and you write as many arguments as you specified in your type. And after the equal sign, you put the result, what function returns. So you can duplicate the name of the function twice. So let's look at an example. Let's create a file called example.hs. And hs is an extension of Haskell files. You put in the Haskell files are called modules. So when you write the file, you need to start it with this keyword module and the name of the module and the keyword where. And the by convention, by naming convention, Haskell modules should have the same name as files. There are some conventions when files inside some directories, there are some naming conventions, but we don't care about this for now. So we have a module example, and we write a single function called increase. We write its name, we write its type, so it's function from integer to integer. And what it does, it takes a number and it increases it by 1. So just we have one argument and we specify only one name. This is what this function does. And how we can now check if it's like correct or if it works? Well, we can, when we call GHCi, we can just pass the path of this function to GHCi, and GHCi will load it, it will compile it, as you can see, and it will check for any errors. So if there are errors it won't compile, it will tell you the errors, but in our case, everything is good. And you see the prompt will change. It will now say this example because you are now in the example module. And if we now call this function increase of 5, we will see that 6. Okay, we wrote our first function and it works. So let's again, if you write the HOF model, and if you just start GHCi, and if you try to increase the number, we won't see this function increase because it's not in scope. GHCi doesn't know where to look this function. So you might happen that you started GHCi and then you created file. What you can do, there is actually a command called load, which is a :L, and you can specify the path to a module, and then GHCi will load this module, and then all the functions that are exported by this module will be available. So this is another way how you can load and check other files and modules. You can actually have your own custom pretty prompt, like not example, not prelude, but maybe some pretty Lambda or something like that. There is a link for GHCi configuration and how you can do this. But in slides, I will always use like prelude or GHCi prompt. Okay, let's talk more about the ecosystem of packages. So we have a function, and then we have now lots of functions or types, and we put them in a single file. So this single file is called a module in Haskell, but now we have multiple modules. So let's say we wrote several files, and we now want to organize them. And if you want to put them in the same idea, you can put them in a package. So package is just a list of modules plus some metadata. For example, who is the author of these modules? So what is this version? What is a short description? And some other metadata. Then there is Hackage. Hackage is a central repository of all Haskell packages. So you can create your own package, you can publish it on Hackage, and other people might use your package if they find it useful. And also you can use packages by other people, and they're taken from Hackage public place. There is several special packages. One of them is Base, and Base is a package for standard Haskell library. It contains lots of modules, which is standard library Haskell, and there is a special module called Prelude. And Prelude is a module containing all functions and types available by default. So this is what Prelude prompt means. When you start file, all the things that are in Prelude module, it is what you can use without requiring any other modules. But not all useful stuff in the Prelude. There are other modules. For example, there is module data.list, which contains other helpful functions to work with this. For example, the sorting function it's not available by default in Prelude. And if you want to bring this to scope, you can just write keyword import and write the name of the module, and then you will be able to use the function. For example, sort function, it orders elements in the increasing order, and there is function nab, which takes all the unique elements of the list. And there are links. You can browse Hackage, you can check modules in Base, and you can see what's in Prelude. So you may be not able to get everything because lots of functions are polymorphic, and we haven't touched polymorphism yet, but maybe nice to browse. Okay, let's dive more into Haskell syntax. So if then else is a construction for creating conditional operations. So let's write a function. I'll start the function with a comment. So single line comments in Haskell start with a double dash. And what we want to write? We want to write a function which we want to improve head. So head throws exception on an empty list, and this is unacceptable. We want to improve. How we can improve? Well, one way we can do this is by creating a function that takes a default element that it can return when the list is empty. So let's create our function called head or default. It takes an integer. So I'm not using integer type, I'm using int. This is like a different representation, more compact, more efficient for memory. But I will use sometimes int because, well, it's shorter. So, but it's a real type. So the function head or default, it takes an int, default value itself. It takes a list of ints and it returns an int. And it should return like either head of the list or default elements. And we give names. So of course, default element called def, and the list is list. And here how we use if. So we check if list is empty. So remember function null, it checks if the list is empty. So if list is empty, then we return default element. Otherwise, else, we return the first element. So here head is the safe function because we already checked if list is empty. So we can safely use head. Also, you can put if then else on different lines, but mind the indentation. So it's maybe helpful when your expressions become bigger and you might want to put them on different lines. And this function works. So we give it an empty list and we get 0. Or if we get non-empty list, we get the first element of the list. So important thing to know is that you always need to specify then and else branches. So it's not possible to like skip then or skip else. In Haskell, it's if then else, it's an expression, and it always must return some value. So you must always return some value, and they both need to have the same type. This is an important thing. So another syntactic construction is guards. And guards help you to write multiple expression, multiple conditions, so you can avoid writing nested if then else. So let's say we want to write the function sign. It takes an integer value and returns a string. It tells whether the number is 0, negative, and positive. And guards is vertical line where you put in the function. So you write a condition and you write what the function should return on the right side of the equal sign of this condition. So if the number n is equal to 0, we return string 0. If the number n is less than 0, we return the string negative, and otherwise we return the string positive. So usually all the guards end with otherwise. This is like a final condition, what the function should return when all conditions fail. And we can see that this function works. And what Haskell does, it checks all the conditions from top to bottom from the first one. And when it finds the first condition that returns true, it just returns a result of this function on this executable condition. This is a nice syntax when you need to check multiple conditions on the start of the function. Okay, so let in is a way to define your own variables in Haskell. So the syntax is the following: you use the keyword let, you name your variable, some name, you assign, you not assign, you say what expression it equals to, and then you use the keyword in and return some result. Or if you want to specify multiple variables, you put them on a separate lines, again, keeping the indentation like consistent. So let's look at an example. Let's write a function. We want to write a function that takes a list and it returns true if the first like 3 elements of the list are equal to the last 3 elements of the list. So let's see, we specify that its type is list of ints, like int put in square brackets. We see that list and we create the variable first 3, which are just the first 3 elements of the list. Okay, it's easy. We have the function take, which takes the first elements of the list. We just assign this variable to the result of, we assign to first 3 the result of applying function take 3 at the list. But how to take the last 3 elements of the list? Well, it's more difficult. There is no function for taking like last 3 elements. But what we can do, we can reverse the list first. We can take then 3 elements. So this will be 3 last, but they will be also in reverse order because we reversed this and then we took 3. So we need to reverse again. So you can see this expression became kind of more complicated. It may be not the most efficient way, but it works. And then after the in keyword, we just compare first 3 elements of the list. And again, we see how it works. If the elements not equal, they're not equal. If they're equal, the function returns true. So it's important to know that in let, there's always, again, must be in. So it's just impossible to just create variables. You need to return something. If you assign variables, there should be purpose in this, in this sense, like you need to use them later. So it's not possible to just create variables. You just define them to some expressions and use later. And you may want to use them when your expressions become bigger. You see this last 3, it's kind of like you call lots of functions itself. And when you have lots of expressions, if you want to use them several times, you might want to create variables to use them. This is when you use let in. There is another way to define local variables or even local functions, which is using the where keyword. And what we want to write now, we want to write a function that takes 2 lists and it returns another list. And what should it take? It should take the last 2 elements of the first list, then the last 2 elements of the second list, and just append those last elements together. Okay, so we think, okay, it makes sense to create a local function that takes a list and returns the last 2 elements of the list. And we use the where keyword and we write the type of this function. It's function from integers. You don't need to write type, but I encourage you to write types in the beginning, and it's usually a good practice to write types of functions and global functions in Haskell. So, okay, we know how to take last 2 elements. We just did this with the previous example, just replace 3 with 2, and we get not last 3, but last 2 elements. Okay, and in our function, we apply last 2 to the first list, we apply last 2 to the second list, and we combine results with plus plus. Easy, and it works as expected. So both let and where are ways to create local variables and local functions. I haven't showed both examples, but actually these both ways can be used for both variables and functions. You can use define functions with let and variables with where. So you might wonder, so which one to use? This looks like 2 ways of doing the same thing, but just with slightly different syntaxes. What's the purpose of this? Sorry, and there is some difference actually between them. I added some links where you can read. So there are mostly difference between scopes, which variables are seen, and other. So it's for now, you may use what you find more appealing, what you like more, what syntax you like more, find more reasonable. But the difference I did sometimes kind of subtle. Okay, now let's talk about immutability. So we learned how to create our own variables. But as I mentioned, Haskell is a mutable language. It means that you cannot change variables, you cannot change values. If it's assigned once, then that's all, it's done. You cannot change. So what does it mean exactly? In GHCi, you can assign some values to variables. We just say like variable list equals to some value, to some list. And we print in, when you do this, GHCi doesn't print anything. So you can just write list again to print its value in GHCi, and GHCi will print it list. But now we want to create another list, where we drop first two elements from our existing list. Again, GHCi doesn't print anything, but if we print our list, we see, okay, it's a list, but without these elements. But if we print the first list again, we see that it hasn't changed. So function drop, it doesn't change initial list, and well, it cannot. In Haskell, you cannot change values, so how this function can even change this? All values are immutable. So you cannot change. All you can do is you can create new values, new variables equal to new values. And you must say, well, but sometimes I need to change things. For example, I have a list of elements and I want to find the sum of all elements. How do I do that? I will create a variable and I will add all values to this. I need to change this value. How could I do this if I cannot change? And the answer is recursion. So if you need to change things, you use recursive function. You cannot change values, but you can pass new values to function, and you can do this recursively. And this is usually how you can update variables. Let's look at an example. So we want to write a function that takes a list and it takes an element, and it counts how many times this element appears in the list. This is going to be so far the biggest function we wrote so far, but so bear with me what it does. So this function count, it takes an integer number and it takes a list, and we want to return also an integer how many times this element appears in the list. So again, we write the number is n, the list is called list. And what we do, we create a helper recursive function called go, and we put it inside the where clause. This is also a common Haskell pattern. So sometimes you need a helper recursive function and you name it go. It's called the go pattern. And this function, it takes an argument which we pass 0 initially. And this argument tells how many times our element appears in the list. So at the beginning, it appears 0 times. So we haven't found any elements so far, and we just appear 0. So what does our function go do? It, again, a result is the number of elements, the number of times n appears in the list, and the list L. So we first check if the list is empty. So if the list is empty, well, obviously there are no more elements in this list. So we just return our result. So you can think that result is kind of calculates how many times we've seen the number n so far. So if there are no more elements in this, just return it. Otherwise, if the list is not empty, we compare the head of the list with our element n. So again, head is a function here because we used null before, and you see that I haven't passed the function n, the value n to this function go, but function go can see n because it's in scope. So go is like local function, and it can see all the arguments you pass to the count function. This is kind of useful when you pass a lot of arguments to the main function, but you need to use only several of them to just have a local function. So we compare the first element of the list with our element, and if they're equal, like that, so yeah, we found our element. So what we do, we call go recursively with increased result. So we just increase the result by 1, and we take the tail of the list. So we just cut the first element of the list. Otherwise, if it's not equal, well, we still haven't found n. So we call go recursively with the same result, but still with tail of the list. And finally, this function will go recursively through the end of the list. So we just cut the head of the list every time, and we finally will get to the list. Of course, if list is not infinite, if list is infinite, we have some problems. So there are better ways to write this function. We will definitely write it better without using unsafe functions like head and tail. But for now, just the way how you think it. So you see, we don't change values, but we just pass new values to the recursive call. And we don't need to change. We don't have mutable variables, just go recursively calls. And Haskell is actually really optimized for this. This is a case of so-called tail call optimization. and it actually doesn't allocate like lots of memory or stuff. It's as equivalent as a loop in other languages, but semantically you need to write recursion, and this function works, which is great. It would be unpleasant if it didn't work. Okay, so final part is higher order functions, which is like the main concept of functional programming. And let's talk of this. So for higher order functions, or in other words, first class functions, is the ability for functions to take other functions as arguments. So in functional programming, functions should be like kind of the same objects as else, like as ints, and you can pass integers or strings or lists to functions as arguments, but why not pass functions? And actually you can. And let's write such functions. So we have a function applied to same. It takes a function and it's put in round brackets. It takes a number, integer, and returns an integer. So it takes only one number, but it takes a function that takes two numbers. So it takes integer, and returns integer. And what we want to do, we want to apply this function to a given number twice. So we give a function, we give a number, and we apply this function to the same number twice. And again, the syntax of calling function is just putting arguments after the space. So there is no special syntax, don't need to worry. It's just the same as for global functions if you pass function to an argument. And we can pass functions, again, without special syntax, just as it is. We pass function div, which takes a number and divides the number by itself. Well, it will always be one, no much sense, but still example. Or if we pass function mod, which takes a modulo of the same number, again, it will always be 0. But if you remember, operators are also just functions. So I can pass an operator plus to the function applied to same. I need to put it in round brackets here, so Haskell doesn't think that I'm not trying to add applied to same and 3. So if it thinks if I'm passing this as a function, I just put it in round brackets, and 3 plus 3 is 6. Or I can pass the operator multiplication. So it will be 9. So nothing special. We can just pass functions as ordinary arguments. Usually, functional programming is associated with Lambda functions, but Lambda functions is not very special. It's just a function without a name. So you're lazy like Haskell and you want to have a function but without name, because naming is one of the hardest problems in software engineering. So we can just avoid creating name, and you can just want to create Lambda function or just anonymous function, a different name on the fly. And the syntax in Haskell for this is just slash and all the variables for this function, again, just after space, then the arrow to the right, and what this Lambda returns. This is just syntax for Lambda functions. Let's see. Let's first write a function, a higher order function that takes another function. So this function satisfies. It takes a function from int to bool. And usually such functions are called predicates. I mean, function from int to bool. If a function returns boolean, it's usually called a predicate. So function satisfies. It takes a predicate, it takes a number, and returns a string. And what it does, it just checks if the given number satisfies given predicate and returns one string. Otherwise, it returns another string. So again, check is just a function, and we can use it in guards. We just call it and it returns bool. And if it's false or true, if it's true, we will get that the number passes check, or if otherwise, it doesn't pass. And we can pass a Lambda function to satisfy. So this is a function from x, and it checks if x is greater than 0. So again, we might just want to avoid creating a separate function because it's just so small. We don't want to create separate function. Again, and what happens? So satisfies calls this function x greater than 0 on 5. Obviously 5 is greater than 0, so the first guard works and we get the first string. But if we pass on a negative number, then we get another string. So nothing special, just Lambda function. So cool thing in Haskell is that functions can actually be partially applied. So let's create a variable div12 by, which is a div applied to 12. And we know the div, if we check the type of div, it's a function from integer and integer to another integer. It takes 2 integers. But if we now check the type of div12 by, we see it's now a function from integer to integer. We applied function to one number and we get another function as a result. So just partially applied, and we can apply div12 by 3 and we get 4 because we just will divide 12 by 4. This is really neat because you can apply partially functions, then you can reuse them. You can specify some arguments in advance. And what is even cooler is that you can do the same with operators. well, for operators, you can, because as I remember, operators just functions, but for operators, you can put the element on the left side of the operator or on the right side. For some operators, it doesn't matter. For example, multiplication, it doesn't matter where you put it, because 3 multiplied by something or something multiplied by 3, it will be the same. But for some operators, it matters. And yes, we can use it. Let's write another higher order function. This time, a function takes an function from integer to integer. So it takes one integer, it takes another integer, and what it does, it applies the function to a given integer, and then it applies to the result again. So we just want to apply the same function consecutively to the result of the previous call again. Just apply twice, applying the same function twice. And if we, again, we can pass operator, this is called like operator section, partially applied operator. If you pass this partial function from, so plus, it's an operator or function that takes 2 integers. We apply it partially to 20, and we now get a function that takes a number and adds 20 to it. So now if we pass this function to and number 17 to apply it twice, we'll get 57, because we add 20 to 17 once, we get 37, and we get another 20 and get 57. The same with multiplication. So this basically works. Everything works, and it's kind of neat. And there are some standard higher order functions, which are very useful. One of them is map. So map takes a function from element to another element, from one element to another, and it takes a list, and it applies the given function to every element of the list. So let's say we map function node over the list of booleans, and it will inverse every element of the list. Or again, if we give like operator multiplication and apply it partially to 2, and pass it to map and do list from 1 to 5, we will get list of odd numbers from all even numbers from 2 to 10. Another helpful function is filter. It takes a predicate. Remember what's predicates function that returns a Boolean value, and the list, and it keeps all the elements where the predicate returns true. So it runs this predicate over all the elements of the list, and if the element is true, if the predicate returns true on this element, we keep it in the result. So this is an example where we want to keep only even elements in the list. Or there is this cute hard operator where you want to keep only elements less than 3. You can also pass operators to filters. Another helpful higher order function, any, just checks if there's at least one element of the list that satisfies the given function. So, and it will first stop. So it won't go through the entire list, and it can actually work on infinite lists if there is an element that satisfies first earlier. So again, everything is lazy. Another helpful function is concat map. It takes a list of elements and a function from element to a list. So you have a list of elements, you apply this function, you now have a list of lists, but now it concats. So basically just map and concat, as the name says. It's really helpful. And another helpful function is iterate. It takes an initial element, it takes a function, and it creates an infinite list of applying this function to the initial element of the previous result and the second. So for example, iterate multiplication by 2, 1. It gives you a list of all powers of 2. So 1, 2, 4, 8. And we just get, we use take 10 to get first 10 powers of 2. This is how functions work. And again, as I mentioned, functions are first-class object, and which means that we can actually have them inside containers. So we can pass them as arguments to other functions. So why not have them inside lists? So we have a list of functions, again, because why not? And the first function is multiplication by 2. And we use function head to extract the first element, and we apply it to 5. So 5 multiplied by 2 is 10. Again, no special syntax. Function application is just a space. So we get a head to list, and then we get a function, and we apply it to 5. So it may look like function head takes 2 arguments, but actually it takes 1 argument, but it returns a function, and we just immediately apply it to 5. So yeah, I kind of see that it might be a little bit difficult to understand and kind of strange, but this is what is happening. So if you want to take one thing from this lecture, what's important to remember is that everything is a function. So operators are functions. Applying function to something is a function, partially applying. So Lambda function of functions. A function is a function, obviously. And the function application is also function. Just a focus of functional programming is on function. And this is how it helps you to like compose things. And which is great is that the syntax is actually the same. So you don't need to have special syntax. You just don't, okay, I just put a function, just put space, an argument, and I apply it. And here you go. So everything just works out of the box. So finally, just a recap of GHCi commands. The most important is actually :q is when you finished playing with GHCi, you can actually quit it by typing :q. And I haven't mentioned :I command, which is short for information. If you want to inspect something about functions or operators, you can use it. And this is a list of resources that you might want to read if you want to dive into some topics or if you're struggling with some of the home exercises. And that's all. Thank you for coming to the first lecture. And now I will answer all questions. Whew. So I see that the chat was quite alive, which is great because actually can't see the chat while I'm presenting. And I wasn't even sure that you could see me. All good functions are 4 letters long folder. Well, maybe it's not a good function then. Can the elements in the list be of the different types? No, all elements in the list must be of the same type. So you cannot have like true and the number. This is an important thing. All elements must have them. Better to use take one than double exclamation mark. Well, the types are different. So take returns your list. So if you take one of the list, you will get the list also. Essentially, it will contain only one element, but still the list. The exclamation mark returns an element. So if you just do take one, you still need to somehow extract this element from this. So you need to do again head or something else, like again, double exclamation mark 0. Why is length computed every single time? Because Haskell has a time for this was kind of information cached when you do it once and the list and doesn't change. Well, because it's how lists are implemented. So to give some like more algorithmic background, lists are linked lists. So they don't store like the length inside, and that to calculate the length of linked list, and you need to walk through every element of the list and just increase the length by 1. Again, if you want to have the multiple times the same list, you can just use a let in or where and just compute it once and then reuse the same variable, but you still need to go through the entire list. Is it possible to get element on infinite index then? No, because you need to construct an infinite index first. Good luck with that. If you have an infinite list, how could I get the last element of it? Well, if you try it, the function last will just ham. So it's not possible to do so. Yeah, see some replies around this. Sorry, I'm just browsing through the chat, open to answer people questions. If you maybe have some notes on some slides, feel free to ask questions now. There is, as I mentioned previously, there is delay 20 seconds between what I'm saying and when you're hearing it. So it might be better to ask questions early. Will slides be available to download after the stream? Well, slides are already available online, so you can download HTML, I guess, on this platform. slides, you need kind of to pay to export them as PDF. So if people want PDF, well, maybe interested people can cache in, and I will be able to download the slides PDF. But HTML you can get from now. I think it can be used offline, so it's not really that difficult, but I haven't checked. What's the difference between int and integer? Okay, so integer is actually an unbounded integer type, so it can be arbitrarily long. So if you want to calculate 2 in power 100, 1000, 1 million, 1 gazillion, it will fit into integer, because integer just expands all the memory as long as you want. So because of that, it's like less efficient, but it fits all numbers. Int is a complex. It's like a machine word. How it works in principle between -2 in power 63 up to 2 power 63 minus 1. So yeah, the Haskell documentation says about something this power 29, which is really weird. So way ahead from something standard. But for now, just 64-bit number, the standard int number. Guard is like pattern matching. Well, not really, but I mean, you can think of the syntax sugar for nested ifs and else's. So you just write. You can think of this pattern like kind of checking Boolean values, like a special case of patterns and pattern matching, but not really. Is otherwise a keyword? No, it's actually not. It's just a global variable in Prelude, and it's defined as true. So just a top level variable is true. So it looks like a keyword, and when people find out, we didn't want to tell that it's a standard function. So just don't prevent people from having this joy of 1 year after learning Haskell finally realizing that otherwise is just an ordinary value. Oh, see a lot of thanks. Cool. Thank you all for kind words. Don't worry, the recording will be available later. So if you skip something, if you want to rewatch, you can watch it later as many times as you want. So I see some questions more. Is tabulation important where than else? Yes, as I mentioned at the beginning, Haskell is a layout sensitive language, so it's better to keep the indentation on some else. So sometimes rules can be really tricky to get, some things don't work. And you cannot use the tab character. So tabs are illegal. You need to use exactly spaces. So if you use tabs, you might get weird results. Just use spaces. And suggestion for now, just copy code from the slides. It's verified that it works, and just change relevant parts when you need for now. Later you get kind of intuition, but sometimes index doesn't make sense. So you can try to torture Haskell compiler and play with different syntaxes, and well, you don't want to see this. What is the best or any solution for space leaks cause of laziness? Well, best solution is to write good code, but there are some standard practices which can help you to prevent having space leaks. So laziness, I mentioned the benefits of laziness, that you don't need to like evaluate something you don't need. But the problem with this is that sometimes you can have unobvious space leaks when program consumes more memory than it actually needs because of laziness. And there are some standard patterns which you can use to avoid it. They cover like 95% of the cases. And the rest, there are tools to investigate space leaks. So you can just monitor performance of your program. You see that its memory consumption grows and bigger and bigger. and there are ways to see why it's happening. Well, not always easy, but sometimes. Folder roasting, something I didn't expect from this lecture. Well, we'll get more into folder on the third lecture, where we'll explain folds and other stuff. Well, just you don't always need, and it's not always used when it's actually, because again, because of space leaks, sometimes it's used with something else would be better. And also sometimes, again, it's maybe better to write explicitly recursion rather than using folding function. Well, understanding folding is great, but you don't necessarily need to use it. In other languages, there is usually a limit to recursion depth. What about Haskell? Well, the limit is the sky, as in favorite cartoon movie. So as long as you have memory, there is no limit. And so, yeah, if it fits on the recursion stack, it's good to go. I missed why just number f1 is treated like int function. Sorry, I didn't quite get the question. Maybe you can elaborate and repeat in more details. But for me, type hello will return hello : string in GHCi version 9.2.1. Oh, great that it's finally fixed. We will see why it's string on the second lecture, but string is just a list of characters. So different name for the same thing, potato, potato. What is the preferred type width? Just 4 spaces? Well, if you ask me, I prefer 4 spaces, but there is no like accepted worldwide Haskell style guide. So some people use 2 spaces, some people use 4, some people use 3 because they decided it's impossible to agree on 2 or 4. So just to make everyone unhappy, they use 3. So yeah, you can use whatever you like. I will check your solutions anyway. I just prefer 4. The order of the arguments is unfamiliar to me. Are there any reasons for this? Can you elaborate more about the order of arguments? So what does it mean? Reasons for what? In the type signature, you write just types. The first type is an int, and the second type is a list. And then the arguments are in the same order. So the first type int, so the first variable will have the int type, will name. The second type is list, and the second variable will have type list. So is this order of arguments? What does it mean? Is it necessary to learn some of the math like Lambda calculus or category theory to successfully program in Haskell? No, it is not necessary. I can't reach Learn Your Haskell book from slides URL. Yes, this is actually a problem. Learn for Haskell book became down just before my presentation, maybe a couple of days ago, which is really unfortunate, just exactly when I wanted to start the course. You can find a hide version. So essentially the online version is free. You can buy the book to support the auto-print book, but the online version is free. It's on Web Archive. You can Google it. I will change the slides and I will change the link to Web Archive so you can actually reach it, but it's yeah, really unfortunate that this book went down. It has some pretty bad places, I would say, some offensive wording in some cases, but it's a good complementary material to learn Haskell besides any course. When will we get our homework? Well, you can start now. Instead of listening to my questions, you can go homework. It's already available public in the GitHub repository exercises. So I already finished exercises for the first 3 lectures, and you can start creating, start finishing exercises for the first lecture, because now should be able to have all the knowledge it's required. So just go to the GitHub repository, fork the repo, start coding, open PR, and when you open PR, there is that PR template who mentions current mentors. This is me and my friend Veronica, and one of us will review your solutions. So yeah, the deadline is 1 week. I pinned the message with a lecture time frame, but I guess I'll write another one with the deadlines for exercises. I guess maybe makes sense. And why, when you check the type of number, you get int to int? Sorry, I still don't get it. But when you check type of number, you will get this num and the double arrow num. So maybe it's question for some specific slide. Sorry, guess it's maybe not that easy to find it. Let me check if there are any questions in Telegram. Oh, looks like the memes game is pretty red in the Telegram channel. The Doom is what I'm using right now. Sorry to hear that. I hope you will feel better. Based. Okay, yeah. All questions asking. I get used to write my list filter x greater than 0, but in Haskell I have to pass predicate first and list second way. Ah, I see. So this is just because we defined our function like this. So a satisfies function we wrote in its type signature. So it takes the function as a first argument and the number as a second. If you write your own function, you can just swap the type signature elements in the type signature and accordingly swap the variable names, and you will be able to pass the element first and then the lambda last. So there is no special reason, it's just how you want to write. Cool. So yeah, as I said, the recording of this lecture will be available later. You can start doing exercises for the first lecture. The deadline is 1 week. So the deadline is mostly for you to keep you in good shape. So you will be prepared to the next lecture. As I mentioned, that it's important to practice because you can just watch slides lecture and understand Haskell. It's probably everything is very different. And yeah, see everyone in a week. And meanwhile, you can ask any questions in the Telegram channel or anywhere on Twitter or something like that. Thanks again for coming. See you.